Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Jorge Miguel. Professor Jorge Miguel completed his degree in chemical engineering at the University of Porto, followed by a PhD in chemical engineering at the University of Edinburgh. Since then, he has held full-time research positions at the University of Massachusetts and the University of Porto. He joined Strathclyde in 2013 and is a senior lecturer in chemical and process engineering since December 2020. His research applies molecular modeling techniques such as Monte Carlo and molecular dynamics to understand systems that are important in chemical engineering applications, with the long-term goal of turning molecular simulation into a widely used industrial tool. His research spans areas as diverse as adsorption, material synthesis and characterization, thermodynamics and phase equilibrium, physics of interfaces, and nanotechnology. He has published over 80 articles in international scientific journals and delivered over 30 invited seminars and conference presentations. So once again, welcome, Professor Jorge Miguel. Thank you so much for being here with us, and please feel free to start your presentation.
Thanks, Larissa, for such a kind introduction, and thank you, Fred, for the invitation to give this seminar. It's a really great pleasure to be here and share my recent work. So I'll start sharing my presentation, and if there's any problem, you can't see it or something, let me know. So my talk today is basically going to give you a bit of an overview of an area that we've been researching quite recently, which is related to accounting for polarization effects in predictions of thermodynamic properties when using molecular simulation. So I'll explain in a bit more detail what this means. So the brief outline is this. I'm going to start to introduce by introducing the concept of force fields, non-polarizable force fields, which are widely used, and then problems that arise from using those force fields. Then I'm going to tell you how we can correct for those shortcomings, namely the absence of explicit polarization effects. And then I'm going to go through two examples, recent examples where we applied these concepts. One is in predicting dielectric constant of liquids and mixtures. And the other one is in the area of force field development for predicting solvation free energies. Okay. And then finally, I'm going to finish with some very recent results from development of a new method based on quantum mechanics, molecular mechanics calculations to estimate dipole moments in the liquid phase. Okay, and that's quite challenging, but we've made some developments there, and I'd like to share those with you as well. Okay, so to begin with, every time we use a molecular simulation, we need to determine how the molecules interact with each other, okay? And that's the core of this force field, what we call a force field, okay, or a molecular model. And that basically explains how atoms in different molecules are attracted or repelled by each other. And so when what I tell my students normally is that this is the creative part of molecular simulation, right? So there's the technical part, which is the Monte Carlo or molecular dynamics methods. And the force field development is the creative part in a way, okay? So we normally include all the different types of interaction between atoms into these force field parameters and functions. So the most common force field function is a Lennard-Jones potential, which is written here. And that accounts for repulsion and dispersion interactions between atoms. This is widely known. I'm just recapping this for context. Then if molecules are polar, we also have to account for permanent electrostatics, okay? And we normally do that by assigning point charges to each atom site, okay? Now, the big missing element here is polarization. And the reason is because polarization is a many-body effect, okay? And that's because the polarization depends on the interaction between a given molecule, the response of that molecule, to the presence of the electrostatic field of the surrounding molecules. Okay, so it's an iteration process, right? So one molecule is polarized by another, and that molecule polarizes the first one to begin with. Okay, and so these polarization effects are really time-consuming to calculate, okay? And so even though many clever people have been developing tools to calculate these polarization interactions in a faster way and developing what we call polarizable force fields, which include these polarization effects explicitly, the fact of the matter is that we are still by and large using non-polarizable models because those are faster and more convenient, and they're widely incorporated in simulation software. And so, you know, when we try to break new ground and do ever larger simulations, we still use these force fields as a first approach in any case. So what we end up doing is we end up including these effects of polarization in a mean field sense, in a way, right? And we do that by tailoring or adjusting normally these point charges to also represent implicitly these polarization effects, okay? So these point charges that we use in our models are effective parameters that are designed to, on average, include electrostatics and polarization effects, okay? I'll come back to this point later on in the presentation, okay? So this is just a brief listing, non-exhaustive listing of some force fields, non-polarizable force fields. Most of you will be familiar with at least some of these, okay? And these are widely used, and they've been really at the forefront of a lot of theoretical understanding and developments over the last, say, 30 or 40 years, okay? They've been immensely successful. Now, of course, now we start to see that they have limitations, okay? And so I'm going to go through these two examples where you know, it's pretty clear that there are limitations in what these models can achieve. Okay, so the first one has to do with the dielectric constant. Okay, so dielectric constant essentially measures the electrostatic response of a phase, normally a condensed phase, a liquid. And so I've picked up 4 benchmark studies, relatively recent benchmark studies, where people try to test force fields for their ability to predict, among other properties, the dielectric constant. Okay, and with the exception of this yellow data set here from Fennell, which focuses specifically on molecules with hydroxyl groups, the other 3 are quite general. So they include molecules of different functionalities throughout the spectrum. Okay. And what you can see is that, first of all, there's a lot of scatter, and of course, dielectric constant is a property that's difficult to predict. But it is very clear that there is a systematic underprediction of dielectric constant in the models. Okay, so despite the scatter, there's an underlying trend which is a systematic deviation. Okay, and this is independent of the force field that's been used. So people have used GAF and OPLS, and there's evidence from other force fields that there's this systematic underestimation. And also from the charge set, the method that is used to calculate point charges. For example, you can use the GAF model with AM1 BCC charges or RESP charges. They're quite different ways of assigning these point charges, and you get qualitatively the same behavior. Okay, so I should add also that convergence is not the problem, because these are studies based on very long simulations. And so you know, as Sherlock Holmes used to say, when you eliminate all other factors, what remains must be the culprit. And in this case, it's clear that this is due to missing physics. Okay, and my argument, and that of others, is this is in fact due to the missing explicit account of polarization effects. Okay, again, I'll come back to this later when we describe how we tackle these issues. Okay, the second example has to do with solvation-free energies. In this case, I'm showing some relatively old data from our group, just as an illustration, where we try to predict hydration of different compounds using 3 different force fields, okay? And the experiments are in purple. And you can see that by and large, with some exceptions, when you have monofunctional, simple monofunctional molecules, the models do okay. But when you go to complex multifunctional molecules like ibuprofen or aspirin, then essentially the models are all over the place. Okay. Now, this is anecdotal, so we just looked at a few compounds, but in fact, there is evidence from past blind tests, you know, over a wide range of compounds, and it's clear from those that molecular simulation methods are not doing much better than much cheaper alternatives like Cosmo, for example, or group contribution methods, etc. Okay, and it's perhaps surprising because they're much more computationally expensive in general. Okay, and so there's a you know, a pervasive feeling, I think, in some elements of the simulation community that you know, these models have hit a brick wall. Okay, and they really cannot be improved much more beyond this limit. Okay, and again, my argument is that at least part of that shortcoming has to do with these missing polarization effects. Okay, so now that we know essentially what's wrong, what's the diagnosis, how can we do something about this and actually correct for these missing polarization effects? So to do that, you're going to have to bear with me. I mean, there's a lot of theoretical underlying detail here, but I've tried to represent these aspects in a diagram form. So what I'm trying to represent here is what exactly happens when we take a molecule from the gas phase, so an isolated molecule, and we put it in a condensed phase, right? I'm mostly interested in liquids, but actually the same principles are valid for solid phases, okay? And so just a moment to understand the notation I'm using here. So when I say G or L, that means that the molecule is either on its own or surrounded by other molecules, okay? Like in the liquid phase. And so this has to do essentially with a nuclear contribution to this polarization, or the presence of nuclei of other molecules around the central molecule, okay? So it has to do with the environment that the molecule is experiencing from the point of view of nuclear degrees of freedom. We have another aspect, which is epsilon 0, epsilon infinity, which also has to do with the environment of the molecule, but now has to do with the electronic degrees of freedom, okay? So we can have the molecule surrounded by vacuum, or we can have the molecule surrounded by a bath of electrons, okay? And the reason I'm doing this, I'm separating the nuclear degrees of freedom from the electronic degrees of freedom. In essence, I'm invoking the Born-Oppenheimer approximation, and that's because we can treat these two degrees of freedom separately using theory, and so that will help us account for these effects, okay? The final aspect that's worth considering is the state of the molecule itself. So in the gas phase, the molecule is completely unpolarized, and so I'm representing this by mu g to stand for dipole moment of the gas, okay? But when the molecule goes to the condensed phase, it quickly becomes polarized. And so it's distorted and acquires a different state of polarization, represented here by the dipole moment of the liquid state, okay? So that's the notation. I also want to introduce the mu m as a kind of halfway state between gas and liquid, corresponding to the actual dipole moment of the model that we're using in our simulations. And again, I'll come back to this a bit later. So that's what happens when we take a molecule, take it from the vacuum to the liquid. So we can now decouple this into a thermodynamic cycle like this, okay? So the first step is we go from mu g to mu l, still in vacuum without surrounding molecules. In other words, we distort our central molecule so that it's polarized in exactly the same way as in the liquid state, okay? But it's still isolated. Then we surround it by a bath of electrons, so we're now accounting for the electronic degrees of freedom of the polarization, okay? So it goes from epsilon 0 to epsilon infinity. And then finally, we pop the nuclei of the surrounding molecules and we revert back to the full liquid state, okay? And this step, surrounding the polarized molecule by other polarized molecules, is essentially what we calculate when we do a classical molecular dynamics or Monte Carlo calculation of phase change energies, entropy of vaporization or solvation free energies, okay? And in doing this thermodynamic cycle, I'm following Leonti, Evans, Stuchebrikov in their MDEC model theory, right? Which were the first to propose this thermodynamic cycle. And then introducing this approximation here, which I'll explain in a second. So what I'm going to do now is going through each of these steps in detail and explaining the fundamental theory behind it. So the first is this distortion, okay? So we are taking a molecule in equilibrium in the gas phase, and we're distorting it so that it's polarized, okay? Typically, what happens is that you increase the dipole moment when you polarize the molecule. And of course, you pay an energy penalty, okay? So there's a positive energy difference associated to this distortion because the molecule is no longer going to be in the ground state, in the equilibrium state. It's going to be in a non-equilibrium state because it's distorted, okay? And I think, to my knowledge, the first people to recognize and implement something like this were Berenson and co-workers when they developed the SPCE water model, which is a well-known model and widely used. Okay, and they introduced this. In fact, the paper was called "The Missing Term in Effective Pair Potentials." Okay, and the missing term is this distortion energy. Okay, which is calculated analytically to first order through this very simple formula. Okay. Now, later on, Bill Swope and co-workers developed some more rigorous and more complete expansions of this up to the quadrupole moment, and we've used these expressions in our work as well. Okay. Now, this distortion term will strongly affect our predictions of phase change energies, such as enthalpies of vaporization or solvation-free energies, because we need to account for this in our calculations. And the models, the non-polarizable models, are unable to do that because our molecule essentially is not changing during the simulation. And that was precisely the point of Berenson and co-workers. They essentially added this term as a correction to their predictions of enthalpy of vaporization. Okay. Now, it has no effect on the dielectric constant because once we are in bulk with the surrounding molecules, then this is not a factor. Okay. So the second step, now that we distorted the molecule, we surround it by a bath of electrons. Okay, so we are now taking into account the interaction between this polarized molecule and the surrounding electrons of the liquid. Okay, and that interaction is now favorable because, of course, that's the reason to begin with why the molecule is polarized, because it will interact more strongly with the surrounding liquid. Okay. And so this describes the purely electronic contribution to the dielectric constant. Okay, it is not the total dielectric constant; it's just the fraction arising from electronic degrees of freedom, electronic response, and that's represented by what is called the infinite frequency dielectric constant, epsilon infinity. Okay, and this is an experimentally measurable quantity, as I'll show. And of course, classical non-polarizable models cannot describe this component because, again, there are no electrons. Okay, so we can only describe this implicitly. Now, what we and others have shown is that, in fact, once you add up the distortion, the positive distortion contribution, and this negative favorable electronic contribution, they tend to cancel out to a very strong extent. And in fact, almost exactly cancel out for water, as we show in this recent paper. Okay, but I'll show you some practical examples of this. Okay, so now the final step in our cycle is, now that we have our distorted molecule surrounded by the bath of electrons, we now have to put in the liquid molecules. Okay, and that's exactly what we do now in a molecular dynamic simulation. So we have a molecule, a solute, for example, that we pop into our liquid state, and we calculate, for example, the free energy or the enthalpy difference, which corresponds to the enthalpy of vaporization. Okay. Now, in practice, however, in our classical simulations, we don't use a fully polarized molecule surrounded by a continuum of electrons. What we do is we use an effectively polarized molecule with an intermediate dipole moment μm surrounded by vacuum. Okay, and the key step of this MDEC model is to say that these two calculations are equivalent, in fact. So the calculation we actually carry out in molecular dynamics with an effective model in vacuum is equivalent to a fully polarizable liquid molecule in a bath of electrons. Okay, so another way of looking at this is that, in effect, what we're doing is we're not running a model simulation with the correct liquid phase dipole moment, but we're using an effective dipole moment, which is scaled by, let's say, this factor K. Okay, there's a scaling factor that allows us to represent the correct dipole moment. Okay, so Carlos Vega published a paper not long ago where he used a different interpretation to say essentially the same thing, which is that when we develop a molecular model, what we try to do is to get the best possible representation of the potential energy surface. Okay, because that's what we're mostly interested to predict our thermodynamic properties. However, if some of our properties depend instead on the dipole moment surface, such as the dielectric constant, then we cannot hope to get it correctly because we are trying to effectively fit the potential energy surface, not the dipole moment surface. So to calculate things like the dielectric constant, we actually should be using the true liquid phase moment, not the effective model dipole moment. Okay. And again, I'll show you exactly how we do that to correct the predictions of the dielectric constant. Okay, so before we do that, let's take a final look at the whole path. So we have the experimental quantities, which are here, this top arrow, and then we break that down into 3 contributions, one of which is the classical calculation, and the 2 others are these distortion and electronic effects, which we can account for by using theory. Okay. So now I'm going to show you in practice how we use this to improve predictions of dielectric constant and then solvation free energies and phase change energies. Okay, so first for the dielectric constant. So this formula at the top is the formula normally used to calculate the dielectric constant in molecular dynamic simulations. Okay, so it's basically calculated from the fluctuations, from measuring the fluctuations in the dipole moment, the total dipole moment of our simulation box. Okay, and these are then effectively normalizing factors. Okay, so as I said, this takes quite a long time to converge, especially for polar molecules, but it's perfectly doable nowadays with current computer power. Now, in reality, however, right? So again, let me emphasize that these calculations make use of our model dipole moment, so our effective dipole moment in our classical model. Now, in reality, the experimental dielectric constant should make use of our real liquid phase dipole moment, ML, not MM for the model. So there's a difference here. But also, instead of having this one prefactor here, we have epsilon infinity, which accounts for the purely electronic contributions to the dielectric constant. So these electronic effects are completely absent in classical models, as I said, because there's no such thing as electrons in the classical approximation. Okay, so the final step is this equation here, which just derives from what I showed you before, where we can say that if our real liquid phase moment is effectively the model moment multiplied by a scaling factor, K. Okay, and so we can now combine all of these equations to come up with a very simple way, a simple formula for correcting the predictions of dielectric constant. So epsilon MD is the prediction of a given simulation, right? We apply this scaling factor K and then epsilon infinity, and we get a new predictive experimental dielectric constant that should be more accurate. So how do we do this in practice? First of all, we find the epsilon infinity for each liquid based on the experimental index of refraction. Now, arguably, one could think about calculating these from first principles, and it's certainly possible, but we chose to decouple that and use actually experimental data to obtain our epsilon infinity values. Okay, and then that leaves our scaling factor. So what we've done was we estimated our scaling factor empirically by matching the dielectric constant of one molecule, methanol. Okay, and I'll show you again how we did that exactly. Okay, so we fitted K to one dielectric constant and then tried to predict this for all the other compounds. So let's start by analyzing this phenol data set in a bit more detail, because before we go on to the others. So if you remember correctly, this data set deals with molecules containing hydroxyl groups. Okay, and it's very clear here. You can see that this trend of underestimating, systematic underestimation, is very clear here. Okay. So what happens now when we start introducing our corrections? So these are the pure predictions from phenol using their GAF model. If we now add the epsilon infinity only, don't apply the scaling factor yet, just for now assume K is 1 and just apply the epsilon infinity. What we see is that now there's an additive change, so that all the data jumps up by a certain amount, which is the epsilon infinity of that particular compound. And you can see already that for low polarity molecules, we are already doing a bit of a better job in predicting the dielectric constant. Okay, but the key, as you will have deduced by now, is to use that scaling factor to correct the dipole moment of the model to the dipole moment of the liquid. Okay, now if we do that, the scaling factor fitted to methanol turns out to be 1.26. If we use that scaling factor, and just so you know, the methanol dielectric constant is this point here that I'm circling. Okay, so that was fitted to match the experiment, but all the rest is now becoming a prediction. Okay, so we completely eliminate all the systematic deviations. There's still a bit of scatter, but it does a much better job at predicting the dielectric constant of all the other compounds. So as a comparison, this plot here shows another model used by Fennell. In fact, they've refined the parameters of GAF, both Lennard-Jones and most importantly charges. They've scaled the charges up so that their models would match the dielectric constant, and they used again methanol as a fit. But their predictions are much improved for the dielectric constant. But our empirical correction is even, or theoretical correction, does an even better job at eliminating these deviations. Okay, so this table shows quantitative data for these this data set. Okay, so that's all well and good for that particular data set with molecules that are very similar to each other. What happens now when we apply exactly the same scaling factor? No more fitting parameters whatsoever, just simple predictions, correct the dielectric constant of all these benchmark studies. And what you see is that even though there's still quite a lot of scatter in the predictions, okay, the systematic deviations are completely eliminated. So you can see that in this table here. The values in brackets are the essentially the bias, the mean signed error, and you can see that they're all on average negative for all of these data sets, which indicates systematic underestimation. But when you apply this correction, they are very close to 1 and on either side of 1, and they're very small numbers. And so that means that we've eliminated systematic deviation. Okay, there's still work to do in terms of improving the force fields themselves to predict the dielectric constant of particular classes of compound, but this systematic deviation seems to be eliminated completely. Okay, so we've gone one step further and tried to now predict dielectric constant of mixtures. So the left-hand plots are the original predictions of models in dashed lines and full symbols, and experimental data in open symbols. So we've looked at ethanol water and ethanol benzene here. And as you would expect, the predictions are underestimating the experiment. But once we apply the correction factor, we get excellent prediction across the board. Okay. And so here, what we're doing is, again, there are no fitting parameters. What we're just applying is simple mixing rules from the scaling factor that we've determined for a pure alcohol in the first place. Okay, so we have scaling factor for pure component on each side, and then we just use mixing rules to predict the dielectric constant of every composition. Okay, and across a range of temperatures. So this is kind of robust across different compositions and temperatures. Okay, so that was the example of the dielectric constant. I'm going to move on to the second example, which is how can we incorporate these concepts into force field development and help to improve predictions of solvation-free energies. So just very briefly, as context, the way we calculate solvation-free energies in molecular dynamics and indeed in Monte Carlo is using alchemical free energy transformations. Okay, what that means is essentially that you take a solute molecule surrounded by solvent. So here we take, as an example, a benzene molecule surrounded by water molecules. And then you gradually turn off the interactions between the solute and the solvent. Okay, so you use a coupling, what we call a coupling constant, lambda, and we use this lambda to slowly turn off the interaction between solute and solvent along this path. Okay, and then if we trace this path, we can integrate the path and get the full free energy of the whole process of decoupling the interaction. Okay, and that turns out to be the solvation free energy of that solute. Okay, so how do we now take those predictions from MD and correct them for these polarization effects? So if you remember from that thermodynamic cycle, we now have two additional contributions, the distortion contribution and the electronic contribution. Okay, so distortion is unfavorable. So when you go from the gas to the liquid, it's a positive energy. And the electronic is a negative energy because it comes from favorable interactions between the polarized molecule and the surrounding environment. Okay, so if we are interested in vaporization process, right, going from the liquid to the gas, we need to have a negative sign in front of these corrections because we're going the opposite way from my thermodynamic cycle. But for solvation, where we're going from the gas to the liquid or solution state, these quantities have a positive sign. Okay. So the way we estimated these quantities is again through simple dielectric theory. So we use the Berenson expression, but we can also use the slope expression, which is more rigorous and exact. And for the electronic contribution, we use a simple Kirkwood-on-Sager dielectric continuum. But again, we played around with these continuum methods, and you can use basically any dielectric continuum model that you want. This one's particularly useful because it's simple, and you can get an analytical formula for it, which is quite appealing. Okay, so as inputs to this, and I'll come back to this point later on, we use the polarizability of the liquid, the dipole moment of the molecule in the gas phase, the dipole moment in the liquid phase, and the epsilon infinity, which is the infinite frequency dielectric constant. So we've applied these as pure corrections to the predictions that we've done with the trap model for alcohols and mixtures with alkanes. Okay, so one aspect of this is how can we correct predictions from an existing force field and make them better? But then what we also did was we used this concept to develop a new model, to parameterize a model from scratch, which we call POLCA, for polarization consistent approach. And so introducing in a way a new paradigm, a new approach to force field fitting, okay, which actually takes into account these explicit effects of polarization. So before we look at the actual predictions of properties, it's interesting to see, to look at the magnitude of these polarization correction terms, okay? So the red group here are polar molecules dissolved in themselves, okay? So water in water, methanol in methanol, etc. And you can see for these systems with polar solids and polar solvents, you have very strong distortion contributions, positive, and very strong electronic contributions, negative. And essentially what happens is that you take two very large numbers with opposite sign and they eventually cancel out to a very large extent. Okay, and so the total correction to polarization is practically zero in most of these cases. Okay. Now, if you take the blue group, these are now non-polar molecules, alkanes, for example, dissolved in polar solvents. Now here, because the solid itself is non-polar, then both contributions, distortion and electronic, are very close to zero, right? And so the total correction is zero. That you expect that to happen because the molecules are not really polar to begin with. In fact, a lot of these molecules are represented by models that don't even have charges. Okay. But the most interesting group is this green one. Okay. Now what happens here is that you have polar molecules dissolved in non-polar solvents. And now things change because the electronic contribution is very similar to the red group. So methanol as a solute has the same kind of or similar kind of interaction with the solvent, with the electronic degrees of freedom of the solvent, regardless of what solvent we're talking about, okay? Because it's still a bath of electrons moving around. Now, what changes a lot is the distortion term, because now if we have a non-polar solvent, it's going to polarize the solute to a much less extent than if you had a polar solvent, okay? So the distortion contribution magnitude is much smaller, and the whole thing is dominated by electronic effect, and the correction turns out to be very strong and negative, okay? And this is going to affect very much the transferability of our model when we go from a parameterization in the pure state to predicting solvation free energies in non-polar solvents, okay? So let's look at the results of this new model. So the circles in blue are properties that were actually used to fit the force field parameters, okay? The charges and Lennard-Jones parameters of the hydroxyl group in these alcohol models, okay? So we used, so here you can see the density on the left top and the diffusion coefficient on the right top, okay? And both of these properties don't involve any polarization corrections. There's just simple bulk properties that depend on potential energy surface of our fluid, okay? So there's no need to apply any type of correction. It just depends on the actual force field parameters. So the trap model is shown here in black squares and our new POLCA model in red circles. And all that we are showing here is that both models perform relatively well, but we've specifically parameterized the POLCA to fit these properties, and so it does a slightly better job than trap, okay? The more interesting thing is these two properties here. So the bottom left, we have the enthalpy of vaporization, okay? And now remember, because this is a phase change property, we actually have to apply these polarization corrections. Now, it turns out that for pure alcohols, as I showed you in the previous table, the actual polarization correction is very small. And so the trap and corrected trap almost overlap. Okay. And again, we do a slightly better job at predicting these properties with the new Polka model. The dielectric constant, on the other hand, is, as you would expect, significantly affected by introducing these polarization corrections. So the original trap model significantly underpredicts the dielectric constant. This is in agreement with what we showed before. But now if you apply that correction factor, both trap and the Polka model are able to predict the dielectric constant across all the alcohols in this series. Now, more interesting are solvation-free energies. Okay, so these are more tricky to predict. So again, for the self-solvation, so now we're looking at the alcohol dissolved in itself. As you would expect, again, the corrections are small, and so both models do fairly well in predicting this. If we take solvation of alkanes in octanyl solvent, again, corrections are 0 because this is a non-polar solute, and so both models, again, do a relatively good job. Now, the big difference is if you have a polar solute, a polar alcohol, dissolved in hexadecane, which is a non-polar solvent. And here you see that the original force field predictions significantly overestimate the experimental data. Okay, and that hints at a lack of transferability of the force field, because it did really well in the pure liquid properties and enthalpy of vaporization and self-solvation, but it fails when you go and transfer it to a different type of solvent. Okay, now if we do apply the polarization corrections, we do a much better job, right? And if we parameterize, if we use our specifically parameterized Polka model, which was fitted, as I mentioned before, only to these properties, we get an even better agreement with experimental solvation-free energies. Okay, so this concept of explicitly accounting for polarization energy effects improves transferability of a force field over different media, different environments. Okay, and that's something that has really not been addressed significantly in the past. In fact, for example, some years ago, the developers of the Gromos force field concluded that it wasn't possible to have a one-size-fits-all set of parameters that was able to predict solvation in water and in non-polar solvents. And so they ended up having two sets of parameters for those two properties. Okay. Now, what we expect, what we hope, is that this polarization correction approach is going to eliminate the need to have that, because now the force fields will, we expect, be more transferable across different environments. Okay, so I think to conclude, I'm just going to go through a few more slides about this new method we've developed to calculate the dipole moment in the liquid phase. Okay, so first of all, why do we need to do this? And as I hinted before, in all of these polarization treatment that I've presented, we need some quantities as input. Okay, so the polarizability of the molecule, and we can get that from experiments or from quantum mechanical calculations. Both are relatively straightforward to obtain. Okay, so that's not a big problem. The high frequency dielectric constant, again, we got it from experimental refractive index. And again, there are quantum mechanical methods that allow us to calculate that if we need to predict it. Okay, so again, not a big deal here. We need the dipole moment of the solid in the gas phase. Again, we can relatively easily get that from experiments or quantum mechanical calculations. In fact, if you're interested in this, there's some very recent interesting benchmark studies of quantum mechanical methods to predict dipole moments, which show that it is indeed possible to get good accuracy with reasonable computational expense. Now, the tricky property is the dipole moment of the liquid phase, right? And why is that? It's simple, because when a molecule is in the liquid phase, at the quantum level, it's very, very difficult to separate the dipole moment of that molecule from the molecules that are around. So in fact, one might argue that at a quantum mechanical level, you can no longer distinguish that molecule from the surrounding molecules, because we are talking about electrons and protons, okay? And so there's sharing of orbitals, transfer of charge, all of those effects that are really difficult to decouple. Okay, so in all that I've shown before, what we've done was we've used dipole moments calculated from quantum mechanics or ab initio MD calculations, which are really, really quite time consuming. And we, to my knowledge, we only really have values for this property for water and for methanol. Okay. And so if we want to generalize this, of course, we need to come up with a different approach that allows us to predict the dipole moment of a molecule in the liquid phase with a relatively cheap computational method. And that's exactly what we try to develop, this what we call self-consistent electrostatic embedding. So it's based on the QMMM approach, which essentially treats the central molecule or the solute at the quantum mechanical level, and then surrounds that by molecules treated at the molecular mechanics level, okay, so at the classical level. Now, the traditional way of doing this is electrostatic embedding, where the molecules, the surrounding molecular mechanics molecules have fixed charges, normally determined by the model dipole moment, okay. Now, there is an alternative, which is used to use polarizable embedding, where the charges of the surrounding molecules actually respond iteratively to the whole system. But that, of course, as you can expect, is much more time consuming. So what we tried to do with self-consistent electrostatic embedding was to strike a good balance in between those two limits, okay? So do something which is as accurate as possible, close to polarizable embedding, but as cheap as possible, close to electrostatic embedding. So how we did this is through a very simple procedure, a self-consistent iteration process. So what we did was we started with a QM molecule, surrounded it by molecular mechanics molecules. So we extracted all of these configurations from a simple molecular dynamics simulation, right? So this is very fast. And then what we did was we assigned 3 different values of the surrounding dipole moment. Okay, so the charges of the MM portion have different values, Q1, Q2, and Q3. Okay, and as long as you span a wide enough range of dipole moments, this procedure will work. And then we carry out a QMMM, a typical traditional electrostatic embedding QMMM calculation, which is very fast on each of these 3 systems. And of course, as a result, you polarize the molecule in the middle from the presence of the surrounding molecules, and you get one dipole moment mu1 at the QM level, okay? And then do the same for 2 and for 3. So you have 3 dipole moments, okay? Now what we realized is that the dipole moment of the quantum mechanical molecule depends in a very simple, straightforward fashion on the dipole moment of the MM part of the calculation, okay? In fact, there's a nearly linear correlation between QM dipole and the MM dipole. It's not exactly linear, and so we end up using a quadratic fit, but for all intents and purposes, to a good accuracy, you can use a linear fit. It doesn't really matter. But once you do that, once you fit the QM dipole to the MM dipole, then you can find the point at which the 2 dipole moments are identical, okay? And that is our self-consistent liquid phase dipole moment, okay? So essentially, we're cutting short this whole iteration process in which you would self-consistently try to find the point at which the QM and the MM dipoles are equal. We replace that by a very simple set of 3 calculations and a linear fit, okay? And we get this self-consistent. And we've calibrated this, we've validated it against more complicated methods, and this is really quite robust. And we've applied it to water in the first instance, and then to a series of alcohols. And these are the results that I'm showing. So now we are actually able, using this computationally efficient method, to predict the dipole moment of not only methanol, water here in blue, and also methanol here, but also all the alcohols up to decanol. So we're dealing with really quite large molecules, okay? And so what I'm showing here is that the predicted dipole moment in the liquid phase as a function of the inverse dielectric constant of the solvent, okay? So we go from very polar compounds here on the left, water here, for example, all the way to alkanes here in yellow on the right, which are very non-polar, okay? And so the full points and lines are the predictions of our SCEE, right, our QMMM method, which we believe are realistic predictions of the dipole moment. And the open symbols, just as a comparison, are predictions of a continuum electrostatic method, okay? Such as, for example, PCM, okay? And as you can see, the PCM significantly underestimates the degree of polarization, okay? So the molecule, in fact, the alcohol molecules and water are much more polarized in a discrete environment than they would be if you treat the solvent as a continuum. Okay, so this has been shown in the past, but we actually, I think, unambiguously show that there's a big shortcoming here. And the big missing contribution is local interactions between the solid and the solvent. In other words, hydrogen bond formation between the central solid molecule and the surrounding solvent molecules. Okay, and that's completely absent in the continuum calculation, but it's present in our self-consistent electrostatic embedding. Okay, another interesting thing here is that we see that there are two groups of molecules, okay, or of solvents. So these are alcohol solutes in very polar solvents, hydrogen bonding polar solvents such as water and other alcohols, whereas this group here is alcohol solutes again, but in mildly polar solvents, amines and ketones. Okay, so molecules that are capable of forming some hydrogen bonds, but not as extensively as waters and alcohols, which form networks and chains. Okay, so we can see that depending on the hydrogen bond ability of the solvent, you get significantly different degree of polarization. Okay, and all the way to the limit where you have a non-polar, non-hydrogen bonding solvent, which is hexadecane, in which case the self-consistent predictions are the same as the continuum. So everything comes up, under the continuum approximation because you don't have any local interactions of import for the polarization. Okay. So we've recently published this in the Journal of Molecular Liquids, and we're following this up with more extensive calculations to actually try to pinpoint what exactly is causing this degree of polarization. Okay. So I have a final slide just to conclude my talk, where we go back to, now that we are able to calculate these dipole moments of the liquid from first principles, we can try to predict what would be the dipole moment of the model that we should use. And also this scaling factor K, which, remember, we used an empirical approach to calibrate this against experiment, but now we can predict this K from first principles. That's what we're trying to do here, okay? So this mu m would be the halfway dipole moment between, exactly halfway between the liquid and the gas phase, and this K is the scaling factor to predict the dielectric constant. So interestingly, we've done that for water and methanol here, and you can see that the dipole moment, the model dipole moment for water, is almost identical to the dipole moment of the TIP4P 2005 model, which is widely considered to be one of the best classical non-polarizable models for water. Okay, so I think it's no coincidence that the dipole moment is almost exactly matching the TIP4P model, 2005 model. And this model, by the way, all of these parameters were parameterized empirically to try to fit that potential energy surface, as Carlos Vega described in his paper. Similarly, the dipole moment of our Polka model, which again was empirically fitted, is very close to this predicted dipole moment of the model of methanol. And finally, our scaling factor, which we determined empirically from the dielectric constant of methanol, is 1.26, which is again very close to the predicted K of 1.23. Okay, so in a nutshell, what this is telling us is that potentially we have now the tools that enable us to predict these coefficients and these corrections from first principles without any empirical fitting, and then use that in force field development and in improving predictions of classical models. Okay. So to summarize, I hope I've shown you how, first of all, there are intrinsic shortcomings of classical non-polarizable models. So in a way, it's the price that you're paying for the speed of using those models. And that arises from missing physics, namely explicit polarization. But as an alternative to using explicitly polarizable models, which are more expensive, we can use simple analytical procedures and simple calculations to correct for these effects in a post facto way to improve the predictions of thermodynamic properties and improve transferability. Okay, and I've shown you how we develop a new model to predict the liquid phase dipole moments, which again allows us to predict these corrections from first principles. So my hope really is that these insights lead to a different approach to classical force field parameterization, which allows us to have better and more transferable models in the near future. So finally, I just wish to thank my collaborators, Leo and Javier, who are my colleagues who've been working with me on the dielectric constant work. José is a colleague of mine from Aveiro University in Portugal, who is the quantum expert in developing this SCEE model. And Cecilia and Andrew were two of my former PhD students who are now in full-time employment elsewhere. And they were instrumental in developing these polarization correction approaches. Okay. And then we should thank funders, and thank you very much for your attention.
Thank you so much, Professor Miguel Jorge. We are now open for questions. If you want to ask one, you can feel free to enable your microphone. And if you're seeing this from YouTube, you can also ask questions using the chat. So who wants to be the first one? You can go ahead, Professor Fred.
Are you listening to me?
Yes, now yes.
Okay, okay. Thank you, Miguel, for this very nice presentation and very exciting results. Let me ask you something. One is, I expect that this scaling factor be more substance dependent. And it's amazing that it's about to be very close to universal, at least for these two examples that you calculate. But it seems to me not expected. I don't know if I'm wrong, completely wrong.
But actually, you are correct. Okay, so let me show you the result here, right? So you can see this, yeah? So this is when we apply the same scaling factor to all compounds blindly, okay? And in fact, it almost eliminated the systematic deviations. Now, it turns out that what we did also was to look at, and this is an extra slide that I didn't have time to include. We looked at compound groups. So we grouped compounds according to functionality, okay? Alcohols, esters, ketones, etc. And what we saw was that essentially there were three groups, okay? These groups here, which tend to be quite polar compounds, they benefit from very similar scaling factors. Okay, they're quite there's some difference here. For example, this last one is 1.38, but really you don't have a lot of compounds, and the statistical error in these is quite significant. So they're all roughly scaled by the same amount. However, there's these other compounds in green here, which tend to be a lot less polar, okay? Ethers, hydrocarbons, etc., where the scaling factor, empirical scaling factor, if we take into account only these compounds, is actually close to 1, okay? So this is something we're exploring a bit more is, okay, now that we can predict this case from first principles, is this the answer we get, right? Is it substance specific just by doing the calculations from first principles, right? That's what we're investigating now. Okay, just to complete this final group of blue ones are the ones where the scatter is so large that we can't tell it. We can't tell which way it's going, right? I mean, these are very, relatively small number of compounds and a lot of scatter, okay? But it's clear that there's these two groups of compounds that, where the scaling is compound specific.
Okay, thank you. Now you have a method that you can calculate this. Oh, that's very nice. Yeah. It's really, really nice. Other question is, you use a target properties like the diffusion coefficient to check the force field. We know that this property is a box size dependent. Did you correct this?
Yes, absolutely. Yeah. You're entirely right. This is box size dependent. So my student Cecilia did all these calculations, and she very carefully checked 3 or 4 different box sizes, extrapolated to infinite box size, and those corrections are employed indeed in these calculations, right? Otherwise, you wouldn't get such good predictions.
Yeah, that's what I was worried about. Thank you. Let people ask, and I have another but.
Do we have another question? You can go ahead, Professor Richard.
I'm clicking all the buttons right now, sorry. Okay, so I've been reading a bunch of review papers lately, and one of them is a review paper by Gubbins in 2016 about polar fluids. He gives an equation there where he shows how you can take a fixed dipole moment and also a dipole-induced dipole interaction and factor that into the Lennard-Jones potential. Are you familiar with that?
Broadly, not that exact paper, but yes, broadly with the concept, yeah.
Okay, so the basic result is that the epsilon and sigma of the Lennard-Jones potential become temperature and density dependent. And so it sort of goes to what you're saying about how it's an effective potential. And so it makes me think that what's happening if you use a Lennard-Jones, like the trap model, okay, as your force field, then, and you tune that to some vapor pressure and liquid density data over some fairly short range from reduced temperature of 0.5 to reduced temperature of 0.9, let's say, relative to the critical temperature. What you're really getting then is an average of that liquid sigma and epsilon over that entire reduced temperature range, which is also varying with density.
Yeah.
And so it's a kind of a mean value estimate of the epsilon and the sigma. So then, now what you've said, it makes me think that we could take the mu, the chemical potential, because chemical potential is also a parameter that goes into that effective calculation. So what we should be doing is taking these dipole moments from the SCEE method, putting them into that formula, and then we would get a better representation, more detailed as a function of temperature and density, and instead of just a crude average over the entire range, now we have something that can address how things are varying within the range more accurate. Does that sound reasonable? That
sounds very reasonable, yes. I mean, we haven't really looked at the temperature dependence of this, but yes, yeah. So I don't know if it would improve things, but I'm confident that it will, right? I like to say that.
Yeah, it sounds like it, yeah.
I mean, the thing is also that there is also some more theoretical backing for using this halfway dipole moment, right? So if you do a first order expansion of the polarization contribution, right? The potential energy surface on average, if you use a fixed dipole, turns out to give you the best approximation is given by this halfway dipole moment, right? So that's been shown by Bill Swope, for example. And so, you know, that accounts for this induced dipole effects into the overall average dipole moment of the model, right? And so, like you're saying, it's possible that if you use this dipole moment in those calculations, then you might get a better estimate of the Lennard-Jones parameters. You know, something else that we've been thinking about, but really didn't have time to do it yet. I mean, it's in my future ideas, is to try to fit a non-polarizable model using this paradigm, this approach, to the results of a polarizable model, not to experiment, right? We've been focusing on experiment, of course, but if you have a polarizable model, you can explicitly decompose the different contributions, Lennard-Jones, from polarization, from permanent electrostatics. And so, you know, by doing that, we might gain a bit more insight into how these ideas affect, for example, the calibration of Lennard-Jones parameters, right? But that remains to be seen.
Yeah, so it seems like it might be fruitful, at least, you know, within the SAFT perspective. I'm not saying SAFT is like super accurate or anything, but it has this segmental perspective that you can bring, which says that, you know, you can think of the solution as just independent spheres first, and then connected by a chain or a bonding term. So from that perspective, you know, looking at all the spheres by themselves, or the segments by themselves, it could give you a sensitivity analysis by incorporating this effective representation in the Lennard-Jones parameters to how much you would be able to distinguish, you know, what's the polarization effect, what's the dipole effect, and all of that. So at least you'd get a sense of how, whether it be feasible just in terms of sensitivity. But anyway, so that's just an idea. But one more question, or a couple related question is, so you showed how the effective dipole in the liquid changes if you've got a polar fluid, if you're interacting with another polar fluid like an amine or an alcohol versus a hexadecane. But what if you had hexadecane, and you sort of talked about this, hexadecane mixed with methanol? Because as a function of concentration, then the environment around the methanol starts to look more like it's surrounded by hexadecane, or it's surrounded more like around methanol. And so that effective dipole moment must be changing as a function of concentration, if I'm understanding.
Yeah, that's a very interesting idea. I mean, we might look at that in the future as well. I mean, at the moment we're focusing on pure liquids, but what I would expect is that, see, if you, let me show you the plot again very quickly. So this is what I'm talking about. So what I think is that you have this kind of mean field description of the polarization, which is well represented by this continuum model, right? And that's part of the story, right? So for hexadecane, that's the whole of the story. But then for polar solvents, you have this other component which comes from local interactions, hydrogen bonds, etc. Right? And so what I would expect to see is that when you go from pure hexadecane and you start, for example, you stick in one methanol molecule in the solvent, right? Then that will form some hydrogen bonds with the central molecule. You'll see an immediate jump away from this line, okay? Jump up, but not fully. It won't go to the full methanol. It will go to the full methanol result, I think, once you have at least one solvation shell, right? You may need more, right? You may need two solvation shells, but my instinct at the moment, based on what we've seen, is that as long as you have a complete solvation shell of methanol, then you might have already the full degree of polarization that you'd see in a pure liquid. So in a way, you start to see about this idea of formation of clusters in the liquid also being related to these effects, if that makes sense.
Okay, so this could have a really big impact on infinite dilution activity coefficient.
Absolutely, absolutely.
Interesting. Okay. All right. I think that might be all my questions. Let me just check. Oh, well, I guess it goes without saying that this whole the dipole, the effective dipole then for the liquid would be density dependent as well as concentration dependent, right?
Density, yes, it would be, yeah. We haven't looked at density of the liquid, but we have done calculations for ice as well as liquid water, and you do get a significant difference in the degree of polarization. It's much more polarized in ice than it is in liquid water, and that agrees with experiment. I would expect that as you go, for example, to supercritical fluids, you get a lower degree of polarization. You know, we can also test that, but we haven't.
Okay, yeah, so that sounds like the density effect would be more of a continuum and steady variation and maybe a larger variation overall than the concentration effect, because the concentration effect just happens all at once. They immediately cluster together and bing bang.
Yeah, possibly. Yeah, I would expect that as well.
Okay, very interesting. Thank you.
Professor Gore, you can go ahead.
Oh, thank you, Miguel. Thank you for the brilliant presentation. I'm actually very practical question. So have you compared the speed? So how fast it is compared to polarizable models, and how slow it is to compare to non-polarizable models, if you consider, well, certain representative systems. So what's sort of what are we gaining? Right.
So the I'm going to be cheeky here and say that you're getting this for free. It's not entirely free. The simulations, the underlying simulations. Let me show you the plots. Just so the underlying simulations say here, right, for prediction solvation free energies, they are done with a standard classical non-polarizable model, and they're exactly the same cost. So we take bare predictions, say, from the trap model, and then we apply these corrections. They are post facto corrections. So all we do is an analytical calculation, which can be done in Excel sheet or something, right, for free, essentially, right? Now, it's not entirely for free because we need this input, right? I think, let me find the right slide, yeah? So we need to have the polarizability, the high frequency dielectric constant, dipole moment of the gas, and crucially, dipole moment of the liquid, yeah? And these three are very simple. You can get them from experiment, which is what we did, or you can do quick quantum calculations, which have an overhead, right? So we need to do it once for each fluid. And now that we have this SCE method, we can also do one calculation for each fluid to get this mu L. I think also what we're looking at is that this polarization, this dipole moment of the liquid, can be easily computed for similar compounds once we have one. So if we know the dipole moment of methanol, it's very easy to get dipole moment of all the alcohols in the chain, right? And so you can cut corners here and get these things really, really fast. But yeah, I mean, if you know all these properties, then essentially the correction is a post facto correction, and it has no additional cost in terms of simulation time.
I see. So, but the idea is that you will calculate this for most of liquids of interest and provide it to the community, right? So that
yes, ideally, exactly that, right?
Okay.
Now,
Good.
you know, if you have contacts with funders, then please tell them that's what I want to do, because you know, I really much like to do it. Yeah, it takes time to do this for a lot of fluids, but we'll get there.
Thank you. Thank you.
Next question.
Just a clarification. When you say that you get the polarizability of the molecule in the liquid phase from experimental, you mean that you are using a Clausius-Monte equation, is it?
You can actually. I think I may have misstated that. We use the polarization in the gas phase, which is much easier to do. So that's the polarizability of the solute in the gas phase. Now, the polarizability of the solute in the liquid phase is going to be slightly different, and there's an approximation involved in this. So, you know, because we're moving from the gas to the liquid, in theory, we probably should be using the average of the two, perhaps, right? Or actually, better even, you should be integrating this over the polarizability as well. I mean, I think what we looked at based on methanol and water analysis, we think that doesn't really affect the results in a very significant way. So we're using a simple approximation of using the gas phase polarizability. And again, that's easy to calculate. You can, of course, approximate it using Clausius-Monte expression, and then see how that changes. Again, we did a few preliminary calculations, and it didn't make much of a difference.
Thank you. Okay.
We have a question from YouTube. Luis Germinani says, "Thank you, Professor, for the interesting presentation. And for my question on predicting the dielectric constant for mixtures, you use the experimental refractive index from pure components. What would be the best approach in the case of solution of complex biologic solutes for which it's difficult to find the experimental value?"
So the experimental value of the dielectric constant. Okay, again, I'm going to be a bit cheeky here. The values of the dielectric constant, the infinite frequency dielectric constant. I mean, right, let me clarify this. What we need as an input are the values of the infinite frequency dielectric constant, not the full dielectric constant, only the ones that come from electronic effects. It turns out that, roughly speaking, that value is 2. Right, the number 2. It's 1.77 for water, it's 2.1 for hexadecane, and it's somewhere in between for most of the fluids, right? The electronic response doesn't really depend very strongly on the nature of the fluid. And so it's very straightforward to make an approximation, for example, for the environment of a protein, right? You can say, okay, this is a non-polar environment, maybe it has something closer to hexadecane. This is a polar environment, maybe closer to water, or maybe it's an average of the two. In any effect, it's not going to affect the predictions very much, because if you look at let me show you the equations again. So you'll see here in the dielectric constant equations, right, that the epsilon infinity is an additive quantity, okay? And if you have an experimental dielectric constant which is significant, then having a value of 1.7 or 2.1 here is not going to make a difference at all, okay? This mainly affects the prediction of dielectric constants of non-polar fluids, where the polar contribution is very small, and it's all about this epsilon infinity. But for polar fluids, it doesn't. I hope that answered your question.
I think it's time to wrap it up. Okay, Professor. We're headed to the final announcements.